In this video, I introduce off-road vehicle trajectory prediction using inverse reinforcement learning. Imitation learning uses a inverse reinforcement learning to find the optimal policy from the expert demonstrations. Agent under this policy can imitate the expert behavior. Now we take kinematic features into account so that agent can better predict the probability distribution of the future path. Here, the kinematic features for self-driving include the vehicle position, orientation, and the velocity. For example, a vehicle at a low speed, it can go straight or make the right turn. However, if a vehicle at a high speed, it can only go straight to avoid the accident for the right turn. Now we use a set of expert demonstrations to train the model to find the optimal policy from the expert demonstrations. We use maximum entropy inverse reinforcement learning to find the policy with maximum entropy. So we use a deep neural network to describe the relationship between the states and the kinematic features and the real-world function. Here, theta is model parameters. To use a gradient descent method to update these model parameters, we need to define a loss function. First, we use a real-world function to define the probability over the trajectory state. That means if this real-world over the trajectory is large, then this probability over the trajectory theta is also large. That means this trajectory have more chance to be selected. Here, theta is the partition function. So we define the log likelihood of the demonstrated trajectory as the loss function. That means we use this log joint probability of this p as the loss function. And then from this loss function, we can calculate the derivative of the loss function with respect to the model parameters set. Here, the mu d is a state visitation frequencies from all the expert trajectories. And this E is expected real-world over the state visitation frequencies and the learned policy. Now let's see how can we use the neural network to find the optimal policy from the expert demonstrations. First, we pick samples from expert demonstrations, use as input to the neural network, and we use the initial theta distribution to predict the real-world R. Once we have the real-world R, and then we can use the backward path from all the possible terminal state to calculate this expected Q value and expected V value. From Q and V, we can calculate the policy. And then agent and this policy from its current state propagate all the possible paths until reach the terminal state. Then we calculate this state visitation frequencies, and we compare with the expert state visitation frequencies to calculate this gradient of the loss function with respect to the model parameters. And then we can update these model parameters. Now we use a two-stage neural network architecture to predict the real-world from the input. Here we first pick up a state from the demonstrations as an input to the network. to extract the features in a low dimensional space. And then we pick the kinematic features from demonstrations and put together as the input for the second stage to predict the real-world function. And then we use the real-world function in the reinforcement learning to find the policy pi. And this policy pi agent generates trajectories and calculate the state visitation frequencies, and then compare with the expert state visitation frequencies to get this gradient, and use this gradient to train the neural network until we get the convergent model parameters. We find the final real-world function. From this real-world function, we use in the reinforcement learning to find the optimal policy with the maximum entropy. And then the agent can imitate the expert behavior. For more details, please check with this reference. Thank you. Bye.